Hello and welcome. This is Vals from the Global Tutor, and today we're going to do a very quick video where we're going to be discussing the forces which act on an electron which is moving inside an electric field, and we're going to use our understanding of the forces which act on the electron to enable us to get an expression for the trajectory or the path which the electron is going to follow. And this is going to be a very general type of discussion. We're not looking for a specific answer. We're not answering a specific question. We're just going to talk about the physics which is at play for an electron which moves in an electric field. And so I've got a setup in front of me here where I've drawn a typical example of how such an electron may be arranged and how the field might come about. We have got a set of XY axes there, and that's just to enable us to know which is the X direction and which is the Y direction. And then we've got an electric field which is directed in the Y direction. So this electric field is directed upwards over there, and we call it EY. We've got our electron, and in this setup, the electron has got an initial velocity Vx. So Vx shows the velocity vector of the electron at the beginning of time. So when we start looking at this situation. And what I've done is I've drawn in two parallel plates. Now those could be two parallel charged plates, for example, two capacitor plates. And these two plates are just drawn in to show how we could set up an electric field in this direction. So if we had a conducting plate here at the bottom, underneath the x-axis, which was connected to a positive potential, and then another conducting plate above the x-axis, which is connected to ground or a negative potential, then what we could get is we could get an electric field which is directed upwards. And remember, the direction of an electric field is the direction of the force which would be experienced by a positive charge which was placed inside the field. So straight away, if this electric field is upwards, then we know that this electron, because it's got a negative charge, is going to experience a force which is downwards. I'm just going to call that F. I hope that all makes sense and we're all on the same page. So that's the setup that we've got. We're now going to go into a discussion about how we can apply what we know about electric fields and physics to this scenario. Essentially, what we're going to do is we're going to write down Newton's second law as it applies to the electron, because Newton's second law will be able to give us the acceleration of the electron. And once we have the acceleration, we should be able to then write down other equations to show us the velocity of the electron and also to show us the trajectory of the electron, where it's going to be at some point later in time. And what is typical with these kinds of examples is that we'll consider motion in the x direction as being separate from motion in the y direction. And so we'll get equations which apply in the x direction and then equations which apply in the y direction as well. So let's get right into it, and let's start off with the x direction. So in the x direction, what do we know as a fact? Well, we know for a fact that in the x direction, this electron is not going to experience any kind of force because the electric field is in that direction, and so the force is only in the y direction. So in the x direction, firstly, there is no force. And the result of that is that there will be no acceleration. Okay, so in the x direction, what I can write, and this is using the equation v is equal to u, the initial velocity, plus acceleration multiplied by time. What I can write in the x direction is that vx is equal to the initial velocity in the x direction, which is vx, plus 0 multiplied by t. So what we have is that Vx is simply equal to Vx. So the x direction has a velocity which is constant. Okay, so we've established that. If we would like to know where this electron is going to be at some point later on in the x direction, then what we can do is we can apply the equation S is equal to ut plus 1/2 at squared. And that's the general equation which gives the displacement of a body at a certain time t if the acceleration of the body is a. Applying that in the x direction, what I get is I get a position x is equal to the initial velocity in the x direction, which is vx, multiplied by t. Now, because there's no acceleration, all of this part of the equation, which is 1/2 at squared, that all disappears. Okay, so this equation, which I'm going to call equation 1, gives us our trajectory in the x direction. So it tells us where this electron is going to be at some point later in time in the x direction. Okay, and we can go back to here, this diagram, and we can say what we know is that this electron, if it experiences a force which is going to be in the downward direction, is going to follow some kind of path like this. So at some point later on in time, it might be there, the force is still going to be in the downward direction. And we know from what we know about physics is that this is the motion which is associated with a parabolic path, because we've got a force which acts at right angles to an initial velocity. And so our position along the x-axis at any time is simply given by the velocity in the x-axis multiplied by the time. So it's uniform motion in this direction, where there's an acceleration is in that direction. So let's go through and then look at in the y direction. And this is going to be a little bit more interesting because there is an acceleration in the y direction. What we can say is, let's take the same equation over there, which is S is equal to ut plus 1/2 at squared. And let's apply that equation to that y direction. In that case, our S becomes y, and that's equal to our initial velocity in the y direction, which is 0, plus 1/2 our acceleration in the y direction multiplied by t squared. Now what we'd like to do is we'd like to get an expression for that acceleration in the y direction, that a. We can get to that acceleration in the y direction by considering the effect of this force over there, because that's the force which acts on the electron. Now that force F is related to the electric field by the following equation. The definition for electric field is that the electric field strength is equal to the force acting per unit charge. Therefore, the force which acts is equal to the electric field strength multiplied by the charge, which is Q. Applying that to this situation, what we then have is the force is equal to the electric field strength, which is EY, multiplied by the charge, which is minus E. So straight away we can simplify this to give us the force is equal to minus E multiplied by EY. All right. So in order to continue, I'm going to need a little bit more space. I'm going to clear this side of the board. This force is the force which will accelerate this electron in the y direction. So this force is actually equal to mass of the electron, me, multiplied by the acceleration. We can rewrite this equation with the acceleration being the subject, because remember, we want to put this acceleration into that equation so that we can calculate the trajectory, that's the position at a later time in the y direction. So this gives us that our acceleration is equal to minus E multiplied by the electric field EY divided by the mass of the electron. And substituting that into this equation gives us the y position is equal to 1/2 multiplied by the acceleration, which is minus e, multiplied by the electric field strength, Ey, divided by the mass of the electron. And simplifying that, we get y is equal to minus e Ey divided by 2 times the mass of the electron. That equation will give us the y position, where this electron is in the y direction at any later time. All we need to do is just remember that we had a t squared there, t squared, and copy that t squared into there. So using this equation, we can establish where this electron is in the y direction, and using this equation, number 1, we can establish where it is in the x direction. So I'll call that equation equation number 2. So what we could do is we could independently use any one of these equations to find where this object is along the x-axis and along the y-axis at any later time. So even if we were to look at the time corresponding to, let's say, that position, we would get an x value which would be over here if this axis was extended, and we'd get a y value which would be over here. It would be in the negative y. So that completely solves our trajectory question. And this applies as long as our conditions which we had apply. So the electron only at a velocity in the x direction. Some interesting things happen if the electron has got a velocity in the y direction as well, but you can use the same principles to answer that. And we're looking at this, of course, in 2 dimensions. We could also look at it in 3 dimensions. That would also be a little more exciting if there was a velocity either coming out of the page or going into the page. But the principles which would apply are essentially the same. For whatever direction we're looking at, we'd look at the force which is acting in that direction. We'd use the force to get the acceleration, and then we would put that information into this equation, which gives us the position or the displacement at some later time. So I hope that was of interest, and if you've had a problem or seen an example which uses that kind of setup, I hope that this helps you to solve it or understand it a little bit better. This is Vels from the Global Tutor. If you like what you've watched, please subscribe to our channel. We upload videos like this all the time. Any questions that you may have in physics which we can answer, I'd be happy to put together a video for you, just for your own benefit and for the advancement of the understanding of physics. Have a lovely day.